recall something about Cal1 because it's confusing. Cal1 and Cal1 we determine, for example, maximum, minimum. However, we have two options. Suppose that we have the problem without constraints. What means without constraint? Okay, there are no limitations in the domain. Suppose x, y. The without constraint means that the domain is all real numbers, no restriction, no interval. Entonces we need to find the maximum and minimum. Suppose one curve like that. Entonces, in order to find the local, okay, this is a synonymous word, local max min, or relative max min. It is synonymous, you know, and the book alternated using this name. So it's easy. You find the critical value, critical value, and the critical value you find when the first derivative of the function is 0 or do not exist. That's the definition of the critical value. In this case, you see we have one critical value number 1. Here, horizontal line, critical value number 2. And here is a sharper point, is critical value number 3, no? Because do not exist the derivative. Entonces, in order to determine if it's maximum or it's minimum, there are many ways to do that. However, in my opinion, the efficiency way to do that is using the second derivative test. O sea, second derivative test. Second derivative test. Entonces, el second derivative test is you find the second derivative and you evaluate in the critical value. Critical value 1, critical value 2, and so on. And critical value 3 maybe, right? But in this case do not exist. So see, the answer is positive. See, the answer is positive. So suppose here is positive. It's positive because remember the meaning or the geometry meaning of the second derivative is concavity. And when it's concave up like that, the second derivative is positive. When it's concave down, is like that. Therefore, we can affirm it with concave down is a maximum. So when the sign of the second derivative evaluate at the critical point is negative number, so say it's a maximum. And when the value of the second derivative evaluate in the critical value is a minimum. I suppose you remember very well this. Yes or no? This is without constraint. Let me analyze now with constraint. Because today we're using this everything but a multivariable. Suppose with constraint. Well, with constraint means okay, we have one specific interval, AB, in which you want to study the behavior of extreme value, maximum, minimum. So we have one theorem important. Okay, the name of this theorem is extreme value theorem. Extreme value theorem. And this theorem say if the function, our function is continuous at close interval a comma b, then exists x6 max min both. But in this case, we are talking about no local, sino global. Okay, these two are global or absolute. They're the same. You know, what is the same synonym? For example, here we are talking about local or relative, and this is global or absolute. And this is easy because global or absolute is, so you take the large value, large, of the function is indicate the global or absolute, whatever you want to, global max. And the smallest value indicate us the global mean. So what is the procedure to find that? Okay, look. This is the most important moment. We have x value. We have restriction, constraints, que es this interval. I don't want the rest. I want to focus my attention in that part. And suppose que my function look like that. Okay, as always, you find the critical value. The critical value is this: critical value 1, critical value 2, and critical value 3. But you don't apply the second derivative. No. You create a list. In this list, you evaluate the function and the critical value, and also in the endpoint. So you evaluate the function and the critical value 1, the function and the critical value 2, this is 3. The function and the critical value 3, and you evaluate the function and the endpoint is A and B, no? A and B. It's obvious. Look in the graph. This is one example. Okay, I created to explain this. This critical value 1 is a global mean, and this B is a global max. But this is the idea, guys. The idea is find the critical value. This is extremely important. When you have the the critical value, you evaluate the function and this critical value, because maybe this relative maximum is absolute maximum, or no? In this case, no. And you evaluate also in the endpoint. Endpoint represents like the boundary of the problem. This is the analysis in single variable, calculus 1. Any questions so far? No? Clear, confusing? Come on, guys. Clear, very well. Now let's move into the multivariable. Multivariable now. A multivariable is similar. So we separate the problem again without constraint and with constraint. We are talking about now without constraint. So no constraint. So what is the algorithm? The algorithm is a multivariable now analysis. Max min. Okay, you find the critical value. Okay, step 1. Find the critical value. Well, the critical value is, okay, you take two derivatives. Partial derivative with respect to x equal to 0, and partial derivative y is equal to 0. Okay. So you find in the original function is given, c is equal f of x comma y. You differentiate with respect to x. You differentiate with respect to y and put it and force it to be 0. And in this moment, we have system of equation. Sometimes the system is horrible for solving because not necessarily linear. Si es non-linear, entonces it's more complicated. But don't worry, because today I want to explain how you solve any system of equation using Wolfram alpha. I don't know now. Okay, so you solving the system. This is the complicated part, the algebra part. It's the complicated part. Now, you apply the second derivative test. Similar to this, second derivative. But the second derivative and multivariable is different. Okay, you compute one thing, it's called d, dx comma y. And dx comma y is f of x, so the second derivative with respect to x 2 times multiplication by the second derivative with respect to y 2 times minus the second derivative x with respect to y. You know, the order is not important, x squared. Okay, the mnemonic divide to remember d is using the terminal, for example, is fxx, fyx, fxy, and fyy. Okay, you multiplication this and this, positive, and multiplication this and this, negative, and you get exactly the same answer of this. So this help me know like one simple second derivative is the combination, the all second derivative of the function. To say if d is positive and second derivative with respect to x, evaluate a specific point, que es a comma b. Now, a comma b is, I suppose, que the solution of the critical value, no? When you evaluate one by one, suppose you have two critical values, you evaluate one by one. See, this situation happen, that means that we have the relative or local minimum. See, d is positive also. Bueno, evaluate at the point, not necessarily x, y. Bueno, at the point is a comma b, a comma b, a comma b. Es negative. Es negative, no, sorry, es positive. Es positive. And the second derivative, this, in a comma b. Sorry, I forgot to say positive here. Now it's negative, is relative max. Okay. Remember, we are working in two variables, or in multivariable. So suppose when this situation happens, is because we have, this is the curve that represents the partial derivative with respect to x, another is partial derivative with respect to y. In this case, both coincident, this is a minimum. This, and like that, is a relative maximum. The only problem is when the discriminant d evaluate at the specific critical value is negative. Immediately when this situation happens, this is saddle point. It's a new idea that you never seen before. Saddle point. I want to explain it what means saddle point. Saddle point is suppose que in one specific point the derivative with respect to the x look like that, and the derivative with respect to y look like that. So what's the behavior of this point? It's a saddle point. In this case was minimal, in this case was maximum, in this case no, was a saddle point. I bring one example in Geogebra to illustrate very well the saddle point. And if the discriminant is 0, que es the last possibility, no conclude. Inconclusive. I don't know. See, this point is maximum or minimum, or I don't know. Okay, let's see first of all the Geogebra to see physically the saddle point, que es a new situation que we never see before. Saddle point, saddle point, saddle point. Look, let me show you saddle point. Switching Geogebra. Okay. Okay, do you see Geogebra now? Okay, look, this is the easy example of the hyperbolic parabolic. At 0,0,0 we have a saddle point. A saddle point you see, for example, here. In that direction, the parabola open down. y en that direction the parábola open up. Entonces, this is no maximum, this is no minimum. It's just saddle point. Okay? Okay. Let's do an example to understand how we manipulate this idea in multivariable. Okay. Come back. Come back. Come back. Okay, whiteboard. Okay, let me erase the board. Do you see the whiteboard now? Example one. Example one. Okay, example one is we have a function. The function is x squared plus 5y squared plus x squared y plus 2y cubed. Entonces, what's the goal? The goal is find the critical value and determine if it's maximum, minimum, or saddle point. Okay, so you determine, for example, first the partial derivative with respect to x. Remember, one more time I explain. When you differentiate partial derivative with respect to x, you consider that x is a variable and y no. Y is a constant. Entonces 2x minus 2xy. The derivative of this is 2x, derivative of this is 0, derivative of this is 2xy, and derivative of this is 0. And you enforce it to be 0. Because my goal is find the critical value. Likewise, when you partial derivative with respect to y, this is 0, this is 10, 10y, plus x squared, okay, this, and this is 6y squared, equal to 0. And now in this moment we have two equations, 1 and 2. We have the system of equations, non-linear system of equations. Always this is a challenge. Don't worry, relax. Because in this moment I want to do by hand. But in another problem, more complicated, I want to do using Wolfram alpha. This is super easy. So don't worry for the algebra. The algebra is not important for us. Okay, so now, for example, I take the first equation. So what is the idea que es crazy? The idea que es crazy is que there are no rules. Solution for the non-linear system of equation algebraically have no rule. In linear, yes, elimination, substitution, but in this case, no rule. So we need to combine, depending on the problem, there are no recipe. Si es elimination, substitution. For example, I take the first equation, that in my opinion is the easier, y hay factorization to x. Wait. It's a plus, no? This is plus. Let me see. Derivative with respect to x is plus. This is plus, is plus. I don't know why I put minus. Hello. Es plus. Entonces, you factorization to x equal to 0. Es obvio que we have two solutions. X equals 0 and y equals -1. Okay? Because you apply the zero factor property, these two is completely irrelevant. X is 0 and y plus 1 is equal to 0, y -1. Now, suppose at x equals 0, use substitution and the partial derivative with respect to y is this. So we have 10y, x is 0, disappear, plus 6y squared equal to 0, and we have one equation that depending only of the y. As you factor out, for example, you factor out to y, we have 5 plus 3y equal to 0. Es obvio que y is 0 and y is equal -5/3. Is the solution for this linear equation. Likewise, this is assumption que x is 0. Assumption y is -1. Substitution again in the y and the partial derivative with respect to y equals -1. Y equals -1 is -10, because I suppose que y is -1, -10, plus x squared, plus 6, no? Because y -1 squared is +1 times 6 is 6. So we have equation que es x squared minus 4, no? Equal to 0, x squared equal 4, square root both sides, plus or minus, x is equal plus or minus 2. Okay, so we have a lot of solutions. Wow. Well, one solution is, for example, 0,0, so 0x, 0y. Look. Okay, I listed the point, the critical value. Critical value here is 0,0. Where come from 0,0? X0, y0. Okay, it's the same conclusion, no? Another critical is 0, -5/3. Okay, it's 0. I plug it in here, I get that value. -1 and y, -1 and 1 is 2 and -2. So another point are 2, -1 and -2, no? -1. Okay, do you understand where I come from this? Okay, we have two values, x, y. For x equals 0, I get two values of the y, 0 and -5/3. For y equals -1, I get to associate two values of the x is +2 and -2. We have 4. In total, we have four critical values. I need to prove somehow that they are or no maximum, minimum, or saddle point. Okay, everyone follow me so far? I promise. This is okay. What is the problem of the calculus 3? The problem in calculus 3 has a track. So we focus on this, and suddenly we get a huge, big, stupid algebra problem. Maybe you lost concentration in this part. So when you're connecting again with the calculus 3 to say, I'm tired because I spend my whole energy. So that is the reason. I don't care this. I don't care algebra. No, I care. You need to get good results. But there are ways to do that using software. Okay, so now I want to go to the second derivative test. Second derivative test, I found the collection of the second derivative xxx, yy, xy. Okay. Well, this is the first derivative with respect to x. I differentiate again with respect to x. Entonces 2 plus 2y. Everyone is agree or disagree? Now yy. You take this and differentiate with respect to y is 10. Derivative x squared with respect to y is 0 plus 12y. Now xy, well, either way, you take this, okay, differentiate first with respect to x, and you differentiate now with respect to y, no? Entonces, this is 0, the derivative to x with respect to y is 0, and this is 2x. It's 2x. Oh, it's 2x. Okay, entonces if you want to compute the discriminant capital D, x comma y, is the multiplication, 2 plus 2y, multiplication 10 plus 12y, minus this guy squared, 2x squared. Okay, the rest is algebra. You FOIL. You try to combine later. I did that. And the answer approximately is 20 plus 44y plus 24y squared minus 4x squared. Okay, and you evaluate one by one in the point. What point? In the critical value, in the critical point I found before here. So you evaluate D and 0, 0. Substitution, guys. Okay, es obvio que es 20. Es obvio que es 20. Yo evalué D in 0, -5/3, que es the second critical value here. Is 40/3 positives. You evaluate D in 2, -1. Okay, substitution. This is X, this is Y. The answer is -16. And you evaluate D minus 2, -1. And the answer again is -16. Wow. Okay, entonces, for sure, when the discriminant D is negative, ese es saddle point. A saddle point, no maximum, no minimum. Okay, so in order to find the si es minimum or maximum, you take care the second derivative with respect to X only. This is the rule. Evaluate at the specific point, no? Evaluate at 0,0. So we continue this line 0,0. I'm plugging in here. It's obvious que 2, ¿no? Entonces, see, this is positive. And this is positive. This point is a minimum. A relative minimum or local minimum, whatever you want to call it. And the second, que es positive, you evaluate the second derivative double x and the specific point 0, -5/3. And the answer is -4/3. Therefore, it's a maximum, minimum. In order to find the C value associated with this minimum and this maximum, so the minimum occur at the point 0,0, no? And the maximum occur at the point 0, -5/3. But what is the value for the minimum? What is the value for the maximum? You evaluate in the original function. So I list it here, and the original function 0,0. 0 minimum. Okay, you plug it in here. Is 0, -5/3, and the answer is 125/27, que is approximately decimal approximation 4 point something, 4.63. So I evaluate in the original guy. And the side point, curiosity, 2, -1, -2, -1. This is no. This is the minimum, and this is the maximum. Do you understand the procedure? Don't worry. Now I want to show you in Geogebra. I have the simulation, no, of this problem. Any question? Any question? Okay. Conclusion. You find the partial derivative with respect to x, partial derivative with respect to y. You enforce it to be 0, and the solution for this nonlinear system give me the potential. The critical value. To analyze the critical value, you apply the second derivative test. Second derivative test is different to the calculus 1. You computed something, it's called D, que es discriminant, and depending the sign of the discriminant. When the discriminant is positive, so maybe it's minimum or it's maximum, depending the sign of the second derivative with respect to xx. Si es positive, es mínimo; si es negative, es máximo. Y si es negative, the discriminant is saddle point. Okay, let me show you in Geogebra now. Let me see it now. Wait a second. Open. Maximum, minimum. Boom. There you go. Let me see. Okay, it's okay. Let me share the screen. Ew. Okay, guys, look. This is our problem. You see Geogebra? Look, this is the original function. Okay. The only thing I want to illustrate is minimum maximum. Okay, you see, for example, here, minimum is in 0,0, no? Maximum it was 0, -5/3, something 4.63, is this point B. And we have two saddle points. Let me make it zoom to see the saddle point. The saddle point is at the same height as 2, no? It's 3. It's 3. Okay, do you see minimum here? Maximum here. And the other saddle point. Any question? Beautiful, or is really nasty? Huh? Gorgeous. Okay. Okay. Let's move on to the problem. Two constraints. Let me come back again to the whiteboard. Now. Okay, erase the whiteboard. Okay. Suppose now, remember, when we have constraints, we need to create the list. In the list, you evaluate one by one, and you determine what is the large value, and you determine what is the smallest value. Suppose this example 2. Example 2 say you have function x squared plus 2y squared minus xy minus x minus 3y. But this function have restriction, constraints, and the domain for the domain the domain is x vary from 0 to 5 and y vary from 0 to 3. Okay, so you want to make a graph of this way. Let's do it. This is x, this is y. Our domain is 0 to 5, suppose 5 here, and 0 to 3, I suppose 3 here. This is our region. Okay, this point is the point 3,5. This is the point 0,0. This is 5,0, and this is the 0,3. This is our region. I want to investigate what happened inside this region. We respect that function. Remember the idea is always find the critical point, critical value. First of all, you take the derivative, first derivative with respect to x, and first derivative with respect to y. Now, first derivative with respect to x is easy as 2x minus y, because here is y, minus 1 equal 0. And first derivative of the function with respect to y is derivative the first is 0, for y minus x minus 3 equals 0. Let me copy this equation in elegant way. For example, 2x minus y equal 1. Wow, linear equation, nice. Cuando es linear es super easy. And the second is, is is minus x plus 4y equal 3. Okay, this is my second equation. It's a linear system of equations. Super easy, super easy, super easy. Using anything you know to find that. And the solution is x equal 1 and y is equal 1. The point is 1, 1. Okay, 1 point 1, 1 is here. 1, 1. Belong to the region. Therefore, I care. It's important for me. That's the only critic about it. It's the only critic. So now I list the point. Okay, I list the point. The point 1, 1. 1, 1. It's important. But you need to analyze the endpoint. And what is the endpoint? Well, the endpoint, guys, is the boundary. For example, that boundary. Include the corner, that boundary, and that. But let's do it one by one. Suppose x equals 0. Suppose that we navigate on the y-axis, que es x equals 0. Entonces you substitution the original function en 0, y. La substitution, look, the original function. Okay, entonces you suppose que x is 0. Entonces we have only 2y squared minus 3y, no? Yeah, stay alive this and this. This is 0, this is 0 because my assumption is que x is 0. When you navigate for the red part. Okay. Entonces, if you want to investigate the behavior of this, you find the derivative. Suppose that this function I want to call f1 in y, because depending only the y, and the derivative of this is 4y minus 3, I put equal to 0, y I solve this. Entonces, at the point y equal 3 over 4. Because the assumption was I navigate for x equals 0. Okay, not bad. Now we navigate for this. It's similar. In Cal 1, we have two endpoints, A and B. Pero it's just a one-dimension domain. The boundary is a point, 0 dimension. In this case, no. In the case of a plane, R2, the boundary is linear, one dimension. So you reduce the dimension always. Suppose now this line blue is y0. So at y0, my equation, when you substitution y0, y0, y0 stay like that. The function x comma 0 is equal, I want to call the function 2, okay, depending only of the and you differentiate, why not? F2 prime and x is 2x minus 1 equal to 0. X is equal 1/2, and the point is 1/2, comma 0, no? Okay, we have here, look, we have here, that point is located here, 3/4, approximately 3/4 here. We found another point here, okay, 1/2, another point here. Okay, maybe it's a good candidate to be a global maximum or global minimum, no? Because we apply the calculus, no? Differentiation equal to 0, but not necessarily apply the second derivative test. No. Finally, we verification the value for the function in this point, and you take the maximum, global maximum, and global minimum. Okay, well, you navigate for that boundary. Sorry guys, it's too long problem. This is x equal 5. So at x equal 5, you plug in the function 5, y. No? I did that quickly, and the answer is 20 plus 2y squared minus 8y. And the thing I did was replace x for 5, and you manipulate. Okay, 5 here, 5 minus 3 is minus 8, 5 here, 5 is 25, 25 minus 5 is 20, Okay, now you you call this function like f3, okay, depending only the y, no? And you differentiate that function because I want to find the maximum minimum, no? So 4y minus 8 equal to 0. Now solving this, y2. So the point 5,2. 5,2 approximation is like that. Another potential point to investigate. And definitely the last is we navigate for this. This is y equal 3. You know, okay, this is too long, but no big deal. Suppose y3, and you plug in and the function y equal 3. When you plug in, the answer is x squared minus 4x minus 9. They call f and 4 depending only on the x, because I assume y3. When you compute the first derivative of that function, the answer is 2x minus 4 equal to 0. X is 2 again. Or this was y, and the point is the point 2,3. 2,3, I suppose is approximately 5, 2, 3 here. Another point. So we have a lot of points to investigate. We have the first one. It was the result to investigate the critical value. And the boundary including the corner, you create the list, the big list, and you evaluate the function in 1, 1. Where I come from 1, 1, that point. The function in 0, 0. Why, professor, in 0, 0? Because 0, 0 is one corner of my problem. You evaluate, for example, in another corner, guess 5, 0. Here, you evaluate the function in 0, 3. 0, 3 is that corner. You evaluate also in 5, 3. Don't forget the corner. The corner is important. And that's it. No. Don't forget this point, and this point. That you evaluate in 0, 3/4. You evaluate in 1/2, 0. Okay, was the when you navigate on this boundary, the maximum value or the minimum. I don't know, say maximum, minimum. I don't care this. And 5, 2. And 5, 2, and 2, 3. Wow, how many points I need to evaluate? 1, 2, 3, 4, 5, 6, 7, 8, and 9 points. And so this is mechanical. You plug it in. You can do using Geogebra if you want. The answer is minus 2, 0, 20, 9, 14, negative 9 over 8, negative 1/4, 12, and 5. Okay, so what is the global maximum? Well, I suppose the global maximum is this, 20. And occur at the point 5, 0 here. This is the maximum here. And what is the global minimum? Well, negative 2. And occur at the point 1, 1, que occur here. End story. Okay. This is very similar to Cal 1. Okay. Number one, you investigate inside the region. We have or no local max, local minimum. I determined yes, and 1 we determined local. In this case, was minimum. And you need to compare the value for this minimum or maximum. After we navigate for the boundary, but navigate is super easy because you convert the problem from 2 dimensions and 1 dimension, and you apply Cal 1. You differentiate, equal to 0, determine the critical value for this point, and finally, when you have the collection of the any point inside the region and in the boundary and the corner, you evaluate the function, and you determine the smallest and the large. End the story. Any question? Any question? But let me show you the simulation for this problem in the Geogebra. I have here the simulation, I suppose. We see, yes. Okay, look. Open. Extremely valid theorem. Okay. Good. Wait. Let me try. No. It's okay. Share screen. Okay. Wow, no good. Geogebra. Okay, share. Okay. Good. I have that. Do you see Geogebra? No? Do you see yes or no? Okay, I have my function. Look. Okay, I have my function. Look, it's super easy to evaluate because, for example, you define your own function here. Okay, and you want to evaluate a specific point. You evaluate, for example, x equal 1, y equal 1. The answer is negative. So you can do any list you create using this idea. But let me show you something. The surface original is this original. However, the specific surface is inside the domain is this surface. Look, let me show you. Do you see? And in my investigation, I determined the global maximum is here in the point B. Okay, the point B is point B is 5, 0, 20, no? And the minimum is 1, 1, negative 2. Okay, this point. This is the minimum, global minimum, and this is the global maximum. Wow, amazing. And this is the same surface. Look, I have the completed surface, but this is specific, the portion inside the domain. If you want, I send to you this script, because in this script we apply one thing I cannot explain, how we create surface. Look, this command surface. And I promise in the last chapter I explained it in this part. Any question, guys? Do you understand the big idea, the roughly idea? Of course, we have to practice more, no? I promise in the review packet we practice this. Okay, in the review packet we consolidate everything. Okay, one more thing topic today is about Lagrange Multiplier. Okay, Lagrange Multiplier. Okay, this is another way to determine the maximum or minimum when you have constraints. Okay, so suppose we have a function. Suppose we have a function c equal f of x comma y, but we have a constraint. Okay, suppose the constraint is g x comma y equals 0. Okay, this is the function I want to optimize, max min, and this is the constraints associated. Okay, so it's basically optimize, minimize, or maximize this function subject to this condition. Okay. Let me try to explain. This is a completely different idea. It's amazing, in my opinion. Lagrange multiplier. Look, suppose we have a function. This function is a surface like that. So this is the representation for the function c equal f of x comma y. We have a constraint. A constraint represents region. This is g. X comma y equals 0. So basically, my domain is that part. Okay. Let me make a zoom to see more clear one piece of this. Suppose I make a zoom using green color, one piece of this. Entonces, en this zoom, well, you see something like that. This is one piece of the curve. And this curve represents g, x comma y, equal to 0, no? However, the function is surface, you know, something can cover everything in the space. I don't see very well in 3 dimensions, but I suppose that the surface have different value for the c. Okay, so we are discussing what is the relationship between the gradient of g and gradient of f. Okay, gradient of g, is a vector, of course, is always perpendicular to g. So in any point, okay, in any point, suppose any point, this is perpendicular. 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 Perpendicular means that the tangent vector can look like that is 90 degrees. This is gradient g. Gradient g. Gradient g. Gradient g in any point. Okay. Let me try to understand now what happened with the gradient f. That is the reason I need to do another similar sketch. Look, again, this is the boundary. Can represent the function gx comma y. This is a piece of curve. We have different point, 1 point, 2 point, 3 point. But in this case, I want to analyze what is the position for the gradient of f. Suppose in this point, the gradient, suppose, this is supposition, guys. It look like that. Now, this is the tangent vector, no? And the angle in between the tangent vector is acute. Okay, so in this point, I want to call point 1, and the point 1 at 1, the situation is the directional derivative, capital D, of the function f, and the direction of the unit tangent vector is positive. Why is positive? Because I know that the definition of the directional derivative is for any unit vector is the magnitude of the gradient. Magnitude of unit vector is always S1 cosine theta. Si theta is acute, cosine the angle in the first quadrant is positive. That means in this point 1, the function is increasing. This is the interpretation. However, in the point 2, let's see it happen completely different situation. Again, this is the tangent vector. Suppose you say, Professor, where come from this? Well, no, using my imagination, the explanation, I need the gradient of the function look like that. In this case, the angle in between is obtuse. And the point 2, the directional derivative is negative. Okay, when it's positive, it's increasing function. When it's negative, decreasing function. Okay. Entonces, I suppose que increasing, stop, decreasing. Entonces, suppose 1.3 in the middle here. In the middle. And this point, one more time, the tangent vector is like that. Y I suppose que the gradient of the function in this point 3 is perpendicular to the tangent vector, unit tangent vector and tangent vector in general. Entonces es obvio que the dot product is 0. And this is the maximum or minimum. Maximum. This is clear. This is no big deal. This is now. So what is the relationship? We discovered one fantastic property. The fantastic property is in the point when the function is maximum or minimum, the gradient of the function is parallel to the gradient of the boundary. This is the discovery of the Lagrange. And Lagrange formulae this idea like that. Es paralelo. Si two vectors are parallel, no necesariamente the magnitude is the same. No. Entonces, the gradient of the function is equal the gradient of the constraints multiplied by something. They call, or he called Lagrange lambda. And lambda is a multiplier. It's a number. A lambda or K or C, it's a number. It's 22. Okay. Entonces, this is the idea. The big idea for the Lagrange multiplier. How you translate this in one acceptable language? Well, okay. Okay, look. Okay, again, you have a problem of the nonlinear system of equation. Suppose the gradient is partial derivative with respect to x, partial derivative with respect to y. We analyze in 2 dimensions. Lambda, partial derivative with respect to g, with respect to x, so g with respect to x and g with respect to y. Entonces, si this is equal, it's because f of x is equal lambda gx. Okay, I have my first equation. And the second equation is f of y equal lambda gy. Bueno, professor, okay, two equations. But you introduce one more unknown, que es lambda. Entonces, how you solve that? Bueno, you take the constraint. The constraint is g x comma y equal to 0. That is my third equation. You solving this complicated nonlinear system of equation using software, of course. And we get the value. Okay. Let me bring one example. No big deal. Super easy. Let me try to explain definitely Wolfram alpha to solve the system. I want to illustrate after the Geogebra, you see more clear this idea that I try to explain using my skill in the whiteboard, but it's weird. It's weird. Okay, let's suppose this example. I promise you see much better this. I create animation to see this idea. Okay, suppose this elementary example. This is the super easy example, and the review package you see more complicated. example 3. We have 3 examples only in this lecture. Well, we have another maybe, depending on the time. Suppose that the function is x times y. And the constraints is x squared plus y squared minus 1 equal to 0. And the constraint frequently Lagrange put equal to 0. Okay. What is the idea then? The idea is super easy. Look at that. You differentiate f with respect to x, f with respect to y. You differentiate g with respect to x. You differentiate g with respect to y. Well, derivative f with respect to x is y. Derivative f with respect to y is x. Derivative this with respect to x is 2x. And derivative g with respect to y is 2y. So our system of equation is equations. Equation is y equal this multiplied by lambda. The lambda is the Lagrange multiplier. This is my first equation. My second equation is x equal to y multiplied by lambda, of course. X equal lambda times 2y. And my third equation that we need is x squared plus y squared minus 1 equal to 0 or equal 1, whatever you want to call 3. Yeah, I need to focus on the solution of this system. In this case, I want to do in both ways. I do by hand because it's easy. I promise the other is not easy. It's horrible. So in the test, you are doing by Wolfram. But in this case, is, for example, so you divide the equation 1 divided by equation 2, division. Es obvio que the lambda is cancelled out. So y over x is equal x over y. Okay, you divide this divided by this. Y over x cancel out 2 and lambda. And cross multiplication, why not? So say it's like a y squared equal x squared. Therefore, y equal x. Now substitution. Substitution where? Substitution in this third equation. Que es suppose x squared plus y squared, pero y squared is equal x. Entonces x squared equal 1. Entonces 2x squared equal 1. X squared equal 1/2. Therefore, x is equal plus or minus radical 2 over 2. So square root 1/2 is radical 2 over 2. And y is the same. Plus or minus radical 2 over 2. Entonces, I suppose that this problem contains maximum or minimum in that point. But what is maximum, what is minimum? So actually, we found 4 points. 2x and 2y. But it's easy to find the maximum minimum because you plug it in the original function that you want to optimize. Remember, my goal was find the maximum or minimum of this function, subject to the constraints. Okay, so now substitution, similar to the list. I evaluate the function in radical 2 over 2, comma, radical 2 over 2. Consider both positive. So plus. And the answer is 1/2. It's obvious, right? It's 1/2. It's radical 2 times radical 2. Radical 2 over 2 times radical 2 is 1/2. It's obvious. Suppose that both are negative. It's exactly the same. It's 1/2. Good. Suppose que alternating one is positive, one is negative. Entonces suppose que es negative this and positive this. Es negative 1/2. Wow, it's the same value but with negative value. And suppose alternating radical 2 over 2, comma, minus radical 2 over 2 is exactly the same, negative 1/2. Wow. And this point is the maximum, and that point is the minimum. of the output problem. Okay. Let me try to explain now how we can do a Wolfram alpha. Okay, let me try, guys. I go to the Google Chrome. I put Wolfram alpha. Let me try to share this screen with you. Do you see Google Chrome? Okay. Now, Wolfram alpha. You put Wolfram alpha. I open Wolfram alpha. Wolfram alpha have a lot of things: physics, chemistry, engineering. I open algebra. And you select here solution for any equation. For example, the first one. And you put our system. You delete everything. And you put our system. Our system is the first equation is y is equal to to lambda. But I have no lambda. I put another variable. I put L, capital L. Time. This is important. So, and between number and variable, not necessarily the time symbol, but in between variable and another variable, yes, because you don't put time. The Wolfram alpha suppose que L time x together is another variable. Okay, and you separate the equation by space like that, and you put another space. And the second equation is x equal 12 again to lambda. I call L time y, no? Time, don't forget the time. Y, space, and the last equation is x squared, you know, x, this symbol, okay, the shift number 6 is power 2 plus y, the power again. It's my last equation. And that's it. And I finish to type in this equation. I press this button, computer input, waiting some seconds depending on the calculator, and you get the value of the x, y, and lambda also. Lambda and the minimum, lambda is equal -1/2, and the maximum lambda is +1/2. And the maximum, exactly we computed by hand, x is equal, and the maximum of both positive or both negative. And when there is minimum is because we have opposite sign in x and y. Super, we are the best in Miami-Dade College. Do you follow me? Everyone follow me or no? So we always, don't waste the time doing this stupid algebra, because sometimes it's very, very, very hard, beyond the calculus tree, the algebra, the stupid algebra. No, we solve it using Wolfram alpha. There are many ways, not necessarily it's the only way, but I propose this software. It's good. Okay, after that, I want to show you one more thing. I want to show you the idea in Geogebra. Look at that. Open this guy. Okay, the same example I want to see graphically in Geogebra now. And you understand a little bit what is the idea for the, okay. Let me share the screen. Screen share. Wow, no good. Geogebra. Screen share. Cancel. Okay. There you go. Boom. Boom. Do you see that? Do you see Geogebra? Okay, good. Very good. Look at that. Well, I type in the original function, que es f of x, y equal x times y. I type in the constraint, que es x squared plus y squared equal 1. The rest you no important. Let me remove the function. Let me remove the constraint. And this is the curve. And the curve you see 4 point, maximum minimum. Let me try to projecting on the xy plane. An important thing I want you see is that in the minimum or maximum point, the gradient vector of the function and the gradient vector of the constraint are parallel. Do you see or no? And the point now, let me see in the point C now. Parallel, opposite direction, pero parallel. Parallel also, in the same direction. And the direction dependency, the function is increasing or decreasing. Let me restore again the function to understand a little bit. Okay, so do you see that sometimes the function is increasing? In this case, it's increasing, look. But in this case, no, it's decreasing. It's going down. That is the reason that the dot product is negative, no? This is the minimum. Now the function now is increasing because the angle is acute, maximum. Look, it's a maximum. Now it's decreasing. The angle is obtuse. More clear the idea? More clear. Lagrange multiply. The Lagrange multiply is another tool. Yes, help. Lagrange multiply is another tool that we have to understand the optimization problem. And we can apply in different constraints. Okay. I hear that NASA apply Lagrange multiply to design a rocket. Of course, we have a lot of functions that need to optimize, and we have a lot of constraints. This is elementary problem. One function, one constraint. We can generalize in the review packet for different constraints. Okay. I suppose I bring another problem. Solving by Lagrange multiplier. Okay, it's the last one. I want to show you the GeoGebra associated with this, and that's it. Okay, let me share the screen, whiteboard again. Okay. I suppose that you see now whiteboard, yes or no? Good. Okay, thank you. 50. Okay, suppose example 1, the last one. What number is example 4, no? Suppose okay, we have function. Okay, I need to optimize, minimize, maximize. 2x plus 2y. Okay. By the way, what kind of surface it is? What kind of surface it is? You see after in GeoGebra. What kind? 2x plus 2y. What kind of surface? I ask the same question because I would like you are familiar when you see. There are another surface that I don't know, but at least the classical that we study, paraboloid, ellipsoid, hyperboloid, etc. You need to identify, no? Cylinder. In this case, what's that? No idea. And the constraints is x squared. Rectangular prisma, no. No, rectangular prisma is no surface. Well, yes, you have surface, pero ese es solid, no? This is surface. It's a plane. This is a plane, yes or no? Plane. Yes or no? It's a plane. How do you know it's a plane? Well, the exponent is 1. It's linear. It's flat. Okay? By the way, one variable is missing, que es z. Okay. So this plane is alone. Let's see. Guys, the next chapter, okay, we need to integration. You need to remember very well this idea. Okay, entonces now the constraint equation is xy plus y squared minus 1 equals 0. Okay, I have no idea. This is maybe cylinder something, but no weird cylinder, no classical cylinder, because C is missing a cylinder. Okay, so you compute the gradient of f. Partial derivative of the function f with respect to x is just 2. Partial derivative of the function f with respect to y is also 2. This is the gradient. A constant. Regarding the point is 2,2. And gradient of the g. Well, partial derivative with respect to x is 2x minus y. Okay, 2x minus y is with respect to x, and with respect to y is 2y minus x. Okay, and you set out the equation. The equation are equation for the Lagrange. Equation for the Lagrange is the first equation is 2, que es this component, is equal lambda this component. This is my first equation. My second equation is this component equal this component. 2 is equal lambda 2y minus x. Equation 2. And what is the last equation? Well, the last equation is the constraints, because you need to go inside this. Entonces, you write like that, or you write like that. X squared minus xy plus y squared equal 1. I prefer it that way. It doesn't matter. So I need to solve in this system of equation. Wow, it's crazy. But no. Using Wolfram alpha, of course. Okay, do it by hand. It's possible, yeah, it's possible, but it's hard. No. I recommend in the test and the homework you use Wolfram alpha for solving linear system of equation. Let's do it. Wolfram alpha. Okay, let me try to share the screen here, over there. No, carajo. Okay, again. Wolfram alpha. Share the screen. Boom. Do you see Wolfram alpha? Oh no. Okay. Guy, open your computer Wolfram alpha and try to type in by yourself this. So don't erase, of course, the word solve, and you type it equation by equation. I go to the restroom now, a little bit. Okay, I'm back. I typing. The first equation is 2 equal what? 2 equal lambda, pero I copy L, capital L. Just in case I put multiplication, but I don't know si es necesario or no. Open the parenthesis. 2x minus y. 2x minus y. Parenthesis, I type in my first equation. I put the space, I put the word and, because I need to satisfy this equation and this equation and this equation. The second equation is 2 equal something L, again, lambda multiplier. This is a Lagrange multiplier. Okay, in the book, normally it's called lambda, but in Wolfram Alpha we call L, capital L. The L time, open the parenthesis, 2y minus x. 2y minus x. The parenthesis. Finally, another and. You put the restriction. The restriction is x squared minus, it's minus, yeah, it's minus. It's minus, be careful, it's x times y. Mandatory the period here, time y, because you forgot time y. Wolfram Alpha believe that x, y together is a one new variable. No. Plus y squared. Equal 1. But did I make a mistake or no? I suppose que no. Everything is okay? You typing similarly like me? All good. Now press the button. Computer input. Boom. Ooh, look at that. The answer is lambda is -2. At the point -1, -1. And lambda is equal to +2 at the point +1, +1. Okay, entonces now what is the rest that you should do? Well, plugging in this value x and y into the original function that I want to optimize and determine who is the minimum and who is the maximum. Okay, let me do. You get the same value like me or no? Exactly the same guy you are doing in the homework. Yeah, exactly the same. Don't waste the time with the stupid algebra. No, it's very, sometimes it's almost impossible. Do it by hand. Okay, the conclusion was que lambda is equal -2 at the point -1, -1. And lambda is equal to at the point +1, +1. Now z value is equal, bueno, 2x plus 2y, ¿no? Entonces, when you plug it in, -1, -1, es obvio que c is -4, and here c is +4. And this is the minimum, and this is the maximum. End the story. We finish. Okay, let me show you in the Geogebra simulation that I have for this problem. Do you understand or no? It's clear or confusing? Okay, let me try to show you as the last part, the Geogebra simulation for this problem. And you see they are perfect coincidence. Okay, not always. Okay, Geogebra have limitation. And sometimes the answer is too weird, and we cannot see very well in Geogebra. But in the majority of the example I bring here, yes, because I create easy example to explain, or relatively easy example to explain. Okay, let me try. Geogebra. Okay, now open what? open this. Okay, there you go. There you go. Okay. Let me share the screen. Boom. Do you see, Geogebra? Okay, this was our problem. Our problem was, remember, we have two surfaces. The first surface is a plane, 2x plus 2y. The second is weird, maybe es, bueno, actually, I predict que es cylinder, pero es a weird cylinder, no circular cylinder, elliptical. And the point que we found belong to the same. So it's common in between the plane and the circular cylinder, no? And you determine that the point are -1, -1, -4, que es this point, is the minimum, A, the point A, look at that, I flash it, the point A, look, flashing, minimum, and B is the maximum, bing. Any question? Super, we are the best in Miami-Dade College, or no? Yes or no? Absolutely, we are the best. Guys, encourage you start doing the homework as soon as possible. Okay, I can extending a little bit. I suppose que I extending no. The homework is to the June 14, no? And the test. Okay, wait a second. I do something. I try to stop sharing. Stop recording.